Welcome to the third installment of our journey through Bayesian inference. We have explored the prior, our initial state of knowledge, and the likelihood, how well our theories explain the data. But there is a third, often overlooked term in the denominator of Bayes' rule, P of B. This is the evidence, also known as the marginal likelihood. While it might look like a simple normalizing constant, it is the most computationally demanding and philosophically profound part of the equation. In its simplest form, P of B represents the total probability of observing the data under all possible hypotheses. Imagine you are testing a new medical diagnostic tool. To understand the evidence for a positive result, you can't just look at the people who have the disease. You must account for everyone, those who have the disease and those who don't. P of B is the sum of these possibilities, weighted by how likely each scenario was to begin with. It is the probability of the evidence, period. Mathematically, this is the law of total probability. We calculate P of B by summing the product of the likelihood and the prior across every possible outcome. If we have a discrete set of hypotheses, it's a summation. If our hypotheses are continuous, like the possible bias of a coin or the mass of a distant star, it becomes an integral. This integral is the total space of our expectations. It ensures that when we update our beliefs, the resulting posterior distribution is a valid probability that sums exactly to 1. Why is P of B so difficult? In high-dimensional problems like climate modeling or deep neural networks, calculating this marginal likelihood requires integrating over thousands or millions of parameters. This is the curse of dimensionality. It is so difficult that for decades, Bayesian statistics was sidelined because we couldn't solve this denominator. It wasn't until the advent of Markov chain Monte Carlo or MCMC algorithms that we learned to bypass the direct calculation of P of B by sampling the probability space instead. Beyond being a math hurdle, P of B is a tool for model comparison. When we compare two different scientific models, we look at their respective evidence terms. A model that is too simple might fail to explain the data, low likelihood, but a model that is too complex spreads its probability too thin across many outcomes, also resulting in a lower P of B. This is the mathematical implementation of Occam's razor. The evidence naturally penalizes unnecessary complexity, favoring the most efficient explanation. Think of P of B as the global surprise. If the evidence P of B is very small, it means the data you just observed was highly unlikely given everything you believed. This forces a massive update in your worldview. If P of B is large, the data was expected, and your beliefs will change only slightly. The denominator is the anchor that keeps the scales of logic balanced. Now, the stage is set. We have the prior, the likelihood, and the evidence. In our final video, we will combine them to reveal the prize, the posterior. We will see how these three forces merge to create the most powerful framework for learning in the known universe. Until then, remember that the truth isn't just about what you see, but how it fits into the total landscape of what is possible. References: David J. C. McKay, Information Theory, Inference, and Learning Algorithms. Christopher Bishop, Pattern Recognition and Machine Learning. Sharon Birch McGrain, The Theory That Would Not Die.